Hello everyone, welcome to our final lab for this semester, the pre-lab. We're going to look at the enthalpy of hydration of magnesium sulfate. Here on the left, this is anhydrous magnesium sulfate. It contains no water molecules. It's a very free-flowing powder. Here on the right, we have magnesium sulfate heptahydrate. It has 7 water molecules involved in the crystal structure. We're interested in, on a molar basis, how much energy does it take, or how much energy is released when we convert 1 mole of anhydrous magnesium sulfate to 1 mole of magnesium sulfate heptahydrate. Let's get some background in first. First, we need to talk about manipulating thermochemical equations. If we multiply both sides of a thermochemical equation by a factor n, we can also multiply delta H by the same factor. And this makes a lot of sense. So here we have 1 mole of ice melting to 1 mole of liquid water. And to do that, we have to input 6.01 kilojoules of energy. Here, if we double the amount of ice, we have to put in double the amount of energy to melt it. So 6.01 becomes 12.02. And if we now go and triple the amount of ice, we now need to put in 3 times 6.01, or 18.03 kilojoules, to melt 3 moles of ice and give us 3 moles of liquid water. All right, everything we're doing today will rely on something called Hess's law. The enthalpy for an overall process can be understood as the sum of the enthalpy values of individual steps. Some reactions are complicated and the delta H cannot be directly measured. For example, we have the reaction here of carbon with O2 to give us carbon monoxide. This is very difficult to do cleanly in the lab because carbon can combine with oxygen to form carbon monoxide, but it also can form carbon dioxide. And so if we want to know what the delta H reaction value is for this, we have to figure it out indirectly. And so we can combine multiple reactions to calculate delta H. For example, here's a reaction that could be provided to us. CO2 breaking down to carbon monoxide, and an oxygen atom requires the input of 283 kilojoules per mole. Taking carbon and reacting with O2 to give us carbon dioxide releases minus 393 kilojoules per mole. If we take these two reactions, CO2 is both a reactant and a product, so we can cancel it out. And we're left with an overall reaction that carbon reacts with half of an O2 molecule to give us carbon monoxide, which is the reaction of interest for us. Now what we can do is simply combine delta H1 with delta H2 here, and we figure out for this process, carbon combining with half of an O2 molecule to give us carbon monoxide, we'll have an output of energy of minus 110 kilojoules per mole. Good way to think about some of these is with a energy level diagram. And here we have now the formation of CO2, and we can think about how it can occur in 2 steps. So we can start with carbon plus O2 to give us carbon monoxide and half of an O2, or a single oxygen atom. The carbon monoxide can now combine with a single oxygen atom to give us carbon dioxide. Likewise, possibly there's a way to directly combine carbon with O2 to give CO2. These 2 processes have to require or output exactly the same amount of energy. And if you sum this minus 110.5 and minus 283.0, you get exactly the same energy doing it directly or doing it in 2 separate steps. Another thing we have to do sometimes in manipulating equations is change the sign of delta H. So we saw this before. This is 1 mole of ice melting to 1 mole of liquid water, and it requires the input of 6.01 kilojoules of energy. However, if we want to go the opposite direction, we want to take liquid water and we want to freeze it to 1 mole of liquid water to go to 1 mole of ice, we need to withdraw 6.01 kilojoules of energy. So this process, liquid water goes to ice plus heat, And so 1 mole of liquid water goes to 1 mole of ice plus 6.01 kilojoules of heat. So here's today's experiment. What we actually are interested in is our anhydrous magnesium sulfate reacting with 7 water molecules to give us our heptahydrate complex. But this reaction is extremely slow, and therefore it's difficult to measure this delta H directly, because this is something that could take days or even weeks to happen under normal conditions. And so we want to use Hess's law to be able to more quickly calculate what happens. What we can do is, instead of going directly from anhydrous magnesium sulfate and 7 water molecules to the heptahydrate, is to start with the anhydrous compound and 7 water molecules and dissolve it. So we take this and we dissolve it in water. This gives us aqueous magnesium, aqueous sulfate, and then the 7 water molecules just add to the aqueous solution. And secondly, we can think about taking these now and arranging these into the heptahydrate complex. Well, we can't do that directly, but we can instead take this and dissolve it to go this direction. So we can figure out the delta H of reaction going from here to here. We can figure out the delta H of direct reaction going from here to here, and we can do this one minus this one to give us the energy of the entire process. So the anhydrous magnesium sulfate plus 7 water molecules plus water as a solvent gives us aqueous magnesium sulfate, and likewise the magnesium sulfate heptahydrate plus water gives us aqueous magnesium sulfate. And so what's going to happen today is you are going to measure this directly, the anhydrous compound reacting with water to give you the hydrated salt, and then you're going to be provided the second delta H. So here's the experiment. Our goal is to measure the enthalpy of hydration of anhydrous magnesium sulfate. Anhydrous magnesium sulfate plus an excess of water gives us the magnesium sulfate heptahydrate, and this is called the delta H of hydration. We can't determine this directly, so we'll consider 2 processes where we can. Again, we take the anhydrous compound, dissolve it in water. We can measure this directly. We can take the hydrated compound, dissolve it in water, and measure this directly. Today, you won't be required to do both. You will measure, in fact, this delta H1, and you'll be provided delta H2 for the reaction. You'll take delta H1 and subtract delta H2, and that will give you the delta H of hydration. We need to talk a bit about, we've been talking about energy in terms of enthalpy. We need to see how temperature changes are related to changes in energy. So when an object is heated or cooled, the amount of energy transferred depends on 3 things: the amount of the object, the magnitude of the temperature change, and the identity of the material that's gaining or losing energy. And we're going to introduce a term here, the specific heat capacity. That's the energy required to raise the temperature of 1 gram of a substance by 1 degree Kelvin. The units of S are joules per gram Kelvin or joules per gram degree C. Either one of those will work here. And here's that equation. So the heat is equal to the mass times the specific heat, which is a constant for a specific substance, times the change in temperature. So Q here is heat. It has energy units, is equal to this mass times the specific heat times the change in temperature. This S is an intensive property, which means it does not depend on the amount of matter present, only the identity of the matter. So water versus copper versus iron, different substances have different S values. All right, the specific heat. The amount of heat required to raise the temperature of 1 gram of substance by 1 degree C or 1 degrees Kelvin, either one's the same. The specific heat is the heat capacity of a 1 gram sample. Its units are joules divided by grams times degrees C. For water, it's 4.184 joules divided by grams times degrees C. Iron is relatively low at 0.444 joules over grams times degrees C. Aluminum, also relatively low compared to water. And most metals are relatively low. If we know the mass of the sample and its specific heat, then the change in the temperature will tell us the amount of heat that has been released or absorbed by the process. So you'll be doing that today. You'll be figuring out the amount of heat that's transferred. Q is equal to mass times specific heat times the change in temperature. M is the mass of the sample. S is the specific heat of the sample, which is a constant. And delta T is T final, final temperature minus initial temperature. Today you'll be using a relatively simple calorimeter. You'll be using a double coffee cup calorimeter. And this is an old version of that. We're going to have double coffee cups. You're going to have a piece of cardboard that's on the top, and you're going to use the temperature probe rather than use the thermometer for this reaction. Your setup's going to look like this: double coffee cup, a piece of cardboard, and then your temperature probe goes down, and your temperature probe will function as both a stirrer as well as a temperature probe. So what are you going to be doing today? One, place 50 mLs of distilled water into the styrofoam cup and lid apparatus. You want to weigh somewhere between 3.5 and 4 grams of anhydrous magnesium sulfate into a weighing boat. Set up the thermal probe via logger probe by clicking the current Chem 111 icon, and you'll click the collect button. You'll place the probe into the water at exactly 4.5 minutes. Carefully pour the entire contents of the pre-weighed magnesium sulfate into the water and stir with a glass rod for 10 seconds to dissolve all of the magnesium sulfate. Put the cover on the calorimeter and stir through the lid using the probe. Keep stirring until the data collection automatically stops at 15 minutes, and repeat for 2 more times. Here's one typical result. So this is your initial 4.5 minutes. You are just letting the probe come into thermal equilibrium with the water and vice versa. And so this is the temperature of the water before you add the magnesium sulfate. And then very quickly after you add the magnesium sulfate, the temperature will spike. And it may look like this. You may get one more temperature point that's here that connects the top to the bottom, or you may not, depending on just exactly when it samples. It doesn't sample every second, and so it may look like it jumps from the bottom to the top. But here's what you're going to want to do with that data. You're going to want to grab the bottom points here and form a trend line that goes across a linear fit. You're going to want to grab these points, the ones that are going up, but not the ones that are coming down. You want to grab these and form a line. And what you're actually going to use for delta T is this bottom line, the distance between it and where this top line hits. You use this to compensate for something that's called thermal temperature loss to the room. You're losing some amount of temperature to the room as this is getting transferred out. And so you're extrapolating up to here to see where this point should be if you weren't losing this thermal energy to the room. So you want to take the distance from this line to this line, and you can go with your cursor in Logger Pro and touch once you put the linear fit, and it'll show you that point. Touch up here, it'll show you that point, and then you can mathematically figure out the difference between those. All right, finally I'll show you a sample calculation. This is for a different system. So for calculating delta H, you need to know the temperature change of the solution, the mass of your solution, so that's the solid solute plus the mass of the solvent, the water, the specific heat capacity of the solution, and the moles of salt that you've reacted. And here's just an example that I've made up for us to go through together. So when 7.85 grams of sodium chloride is dissolved in 50 grams of water, the solution temperature drops by 2.07 degrees C. If the solution has a specific heat capacity of 4.18 joules divided by grams degree C. What is the enthalpy of solution for sodium chloride? And now let's see how these pieces, we can put them into the equation. So when 7.85 grams of sodium chloride is dropped into 50 grams of water. So we want the mass of the solution, and masses are always additive. So 50 plus the 7.85 gives me 57.85 as the mass of the solution. I add those two together. And then the S of the solution was given in the problem, 4.18 joule divided by gram degree C. I put that in here. And then the temperature drops by 2.07. So I need a minus. The temperature change, the temperature went from high to low. So final was lower than initial. And so I have a negative sign here, minus 2.07. I put all that in. I get about 500 joules as the enthalpy of reaction here, or enthalpy of solution. I get about 500 joules. I want that to be in joules per mole, and so what I do is I express how many moles of sodium chloride I had. So 7.85 grams divided by the molar mass of sodium chloride, 78.45, gives me about 0.1 moles of sodium chloride. And so this amount of heat, minus 500 joules, was produced by 0.100 moles of sodium chloride. So 500 divided by 0.1 gives me minus 5,000, which in scientific notation is minus 5.00 times 10 to the third joules per mole. So here are the tips and tricks. Check the coffee cups to make sure there's no holes. So even as people stir these, sometimes they'll poke a hole in the bottom. You want to make sure you don't have holes or any cracks in the bottom, because you'll start to lose solution. You want to use the same two nested coffee cups for all three trials for consistency. You want to get a cardboard with a hole to place on top of the coffee cups to minimize how much heat you're losing to the environment. You want to support the coffee cups with a ring stand so they don't tip over. You want to weigh out 3.5 to 4 grams of anhydrous magnesium sulfate, and you're only weighing for one trial at a time. You don't want to have the magnesium sulfate out in the room. It will pick up humidity, water from humidity in the room. Return the lid to the jar as soon as you're done weighing out the reagent, and this will help keep the magnesium sulfate dry for you and everyone else. Carefully measure out 50.0 mLs of water with the 50 ml graduated cylinder. You want to complete a total of 3 trials, and please be careful not to spill water on the laptops. For waste disposal, all liquid waste is rinsed down the drain, and for cleanup, please clean the glassware before returning it to the drawers. As far as safety, basically the same safety that we always have. Everyone in the lab will wear goggles and lab coat the whole time while in the lab room. You can take a break in the hall from wearing goggles if you need to. You need to keep your goggles over your eyes, not on foreheads or chins. Use water and white towels to absorb any spills. For cleanup and disposal, all liquid waste can be rinsed down the drain. Wash all glassware and return it to the appropriate location. Use disinfectant to wipe down the surfaces near your workstation.